one of the 5 kinematics equations. Now, each of the 5 equations has one of these elements missing. The one we'll look at today has final velocity missing. So the equation for this is as follows. The first question we're going to handle today is the following. The steel cables on an aircraft carrier cause a plane moving forward to decelerate at 15 meters per second squared and come to a stop after 150 meters. How long did it take for the plane to stop? The first thing we're going to do is we're going to note down what we've been given in the problem. The first bit of information we get is that the plane is moving forward and it decelerates at 15 meters per second squared. So we have an acceleration value. Now, acceleration is a vector quantity, and we know the plane is moving forward, so any deceleration value must be in the reverse direction. We also know that the plane came to a stop, so that means we have our final velocity, which is 0 meters per second, which is also a vector quantity, and the plane came to a stop after 150 meters. So we know that our delta D is 150 meters. Now, since the plane was initially moving forward, we know that the displacement must be in the forward direction. And we also know that our final velocity must be in the forward direction. So as you can see here, I've simply rewritten what we were given in the problem. And for the purpose of keeping things consistent, we're going to try and maintain the same direction throughout. So we're going to rewrite acceleration as negative 15 meters per second squared in the forward direction. The next step is to write down what is required of us, and since the question was asking how long it took for the plane to stop, we are actually going to be solving for time. And that's going to be in seconds. Of course, the next step would be the equation that we're dealing with, and we all know this is our equation as follows. Squared. We should normally rearrange for t, which is what we're trying to solve for, but because this equation is more complicated than the other four, we will leave it and rearrange as we solve. Okay, so the next step is to plug in what we know into the equation that we've been given. So we know our displacement is 150 meters, and that is equal to our final velocity, which is 0, times our time, which is what we're looking for, minus half, and our acceleration value is negative 15 as we discussed over there, and we have time squared. Now, what we know right away is that this part over here is automatically 0. So in our next line, we can ignore that. So we now have 150 is equal to negative half and negative 15 t squared. So what we could do now is we can multiply this out. So we have 150 is equal to 7.5 t squared. So that means t squared is equal to 150 divided by 7.5, which is 20, and t is equal to square root of 20, which is 4.47213 seconds, not rounded to significant digits. Now, if we were to go back and look at significant digits, we know we have acceleration, which has significant digits, 2 of them. We also know displacement has 2. So when we come down to our calculation over here, we know there's 2 here and 2 over here. So 2 significant digits means 2 over here, again 2. Dividing by 2 and 2, you get 2 significant digits over here. So square root of that, we are aiming to keep 2 significant digits. So our final answer is going to be 4.5 seconds. So to restate the answer, the plane took 4.5 seconds to stop. The second question that we're going to handle today is the following. The 1968 Corvette took 6.2 seconds to accelerate to 160 kilometers per hour north. If it traveled 220 meters north, find its acceleration. So as usual, we're going to first note down what we've been given in the question. We know right away that the time is 6.2 seconds. We also know that the Corvette accelerated to 160 kilometers per hour north. So our final velocity is 160 kilometers per hour north. We also know that it traveled 220 meters north. So our delta D is 220 meters north. And of course, we're required to find our acceleration. Before moving on to look at the equation, we need to make sure that these units are consistent. Now, assuming we want our acceleration in meters per second squared, this matches because it's meters and the time works as well. The only thing that's wrong is our final velocity, which is in kilometers per hour. So we're going to change it down here. We have 160 kilometers per hour. To convert this, first we're going to convert the kilometers into meters. So we have in 1 kilometer, 1,000 meters. And then we're going to convert our hour into seconds, which is as follows. Now, punching this into a calculator, we get the answer for 44.44 meters per second north. So as you can see here, I've simply written out what we were given and what we were required. So now we will continue with our analysis, which is of course our equation as usual. Which is equal to d minus half t squared. Now to make this calculation easier, we are going to isolate for acceleration right away. So we're going to have acceleration is equal to 2 delta d minus v t over negative t squared. And now we're going to continue with substituting the values we know into our equation. We know our delta D is 220 minus the final velocity, which is 44.44, and our time is 6.2 seconds. And this is all over negative 6.2 squared. So if we continue to solve this, we get 20 . So right now I just simplified this part and this part as well. Our next step is to get rid of this. So you have 2 times negative 55.528 over negative 38.44. Now I'm just going to divide these out right away. So we're going to have 1.445369, and multiplying by 2 gives 2.889074. This is meters per second squared north. Now looking back at significant digits, we're going to go right back up to the top. So we know this has 2 significant digits, And if we look at our conversion over here, since we had two significant digits, we need 2 over here. And we have two significant digits here. So 2 times 2, we're keeping two significant digits. 2. And this is two significant digits, so we're going to aim for 2 over here as well. Subtraction, this is in the tens column, this is in the tens column, so we're going to aim and keep the tens column. And that's one significant digit divided by two significant digits, so we're going to keep one significant digit, which means we only need one significant digit over here. So our final answer is 3 meters per second squared north. So to restate the answer, the acceleration is 3 meters per second squared north.